What's up, guys? My name is Satvik Mojnidar, and I'm probably going to be flying during this time, so this is actually pre-recorded. So hello from the past. Today I'm going to be doing a review of a high-performance brain-to-text communication system that I believe is a state-of-the-art application of BCI. Earlier this year, Professor Shenoy at Stanford broke records in brain-to-text communication with an interesting medium, handwriting. He was published in Nature and he made headlines all across the web. So today we're going to figure out how he broke those records. First, we need to understand what brain-computer interfacing, or BCI, is. BCI is a field of research that aims to understand the brain by decoding neural activity through statistical modeling or machine learning. Currently, there are a couple of interesting areas of research within this field. NeuroPace is treating symptoms of epilepsy with their neuromodulatory device, the RNS system. There's a professor at UT, Professor Jose Del Milan, amongst others, that are doing research in innovating BCI and prosthetics. And obviously, there's the big Neuralink trying to cure Alzheimer's with adaptive stimulation and brain-computer interfaces. So over here, I have a little flow chart to describe at a high level what BCI is like. So as we can see, data is acquired from the brain, and this data is then put through some sort of signal processing script or program. And then this information is then transferred to a BCI application where a decision is made. Simple as that, but we'll be getting a little more specific. We're going to be talking about brain-to-text communication. The main goal of brain-to-text communication is to communicate words to a computer without moving a muscle. This aims to actually aid paralysis patients with the ability to communicate, because if you're paralyzed from the neck down, you're likely not going to be able to type on a computer. Being able to communicate through a computer is hugely useful. Previous strategies actually centered around point and click movement because it was simple. Basically, what you would do is you would control a cursor and click letters that appear on a keyboard, as you can see in this image down below. This strategy involved simple straight line movements and produced a 40 character per minute typing speed at 24.4 correct characters per minute. Dr. Shenoy's lab thought maybe there's another way to do this. The idea was this, that neural activity recordings contain a lot of noise, and point and click representations in neural activity are actually pretty simple. And so if there's a lot of noise, these representations might be too simple to completely isolate and differentiate within the noise. So more complex movements might be actually more efficient to decode within neural activity rather than simple movements. And handwriting was that candidate. So let's look at the data. The data was actually made up of 7.6 hours worth of training data. That's around 31,472 total characters. And this is what the machine learning model that they used was trained on. The recordings were actually multi-unit threshold recordings from 192 electrodes in the precentral gyrus, which is a part of the brain that, well, at least this specific part of the precentral gyrus was largely related to hand movement. The subject themselves was from an intracortical implanted device study, BrainGate. And so he had a surgery to implant this device in his brain, and he was already paralyzed from the neck down. So there was no way that he was going to be writing this physically himself. So the first step was to figure out, is this even possible? Is handwriting actually encoded in our neural activity? They needed a proof of concept. And so what they did was they had the subject write some specific characters over a period of time, and they collected data on that. They recorded the neural activity. And from that, they did a couple of things. They did a time warped principal component analysis to show patterns in activity that are unique to each character. So visually, they could actually see that there were patterns of activity that were specific to each character. For example, a D would have a similar activity amongst all its components to another D, maybe written 2 minutes down the road. And so that was their first hint that maybe this is something we should look into. Next, they did a linear decoding at pen tip velocity to reconstruct the characters. It is a slightly complex process, but essentially they simulated a pen and were able to use the neural activity of movements to actually draw out each character in recognizable characters. And so this is what the paralyzed patient was intending to draw. And as you can see, they closely resemble the actual characters. And so the next thing they did was they used a T-SNE to create embedding to reveal tight clusters of activity for specific characters. So this actually proves that the data is replicable over a period of time for the specific subject. For example, he wrote an M a number of times, and that M was all related to each other according to this mathematical model. So clearly there is some mathematical relationship. The last thing they did was use a K nearest neighbors classifier to classify this activity. They basically were like using this model to predict based on the current neural activity, what is the character being written, and they had an accuracy of 94.1%, which is really promising. But it is important to note that this was all pre-recorded. So the next challenge was to do things in real time. The real-time application was a little more complicated, though really not that much more complicated. A couple important things to note in this flowchart. So the subject is trying to write an R right now at this specific time point. And this data from all 192 recording electrodes is being transferred into a recurrent neural network, which is a deep learning network. And then a probability is being outputted that will say how likely this certain time point is to drawing a specific character. And that is outputted. Yeah, that's pretty much what this figure is telling us right now. So we need to go over what a recurrent neural network is. A recurrent neural network essentially maintains processes sequence of data by maintaining a context of previous predictions. It's a deep learning architecture. It's a neural network. And basically what it does, as you can see, is it'll make a prediction. So the X's are input and H's are output. And so it will make a prediction, but will also record some sort of context. And this history is actually going to be transferred to the next prediction that is going to be made, because likely this input is somehow related to the previous input by time or by some other relationship. And so in that way, the recurrent neural network is able to quantify context, which is really important. Now, the handwriting brain-to-text model is a little more complicated, but I think it's still a recurrent neural network. But I think there are three really important points to pay attention to here. First is firing rate. This is our input. As you can see, there are 192 recording electrodes per time point, and that is what is being input into the model. Our outputs are interesting because unlike our previous recurrent neural network that we looked at, this actually has two different outputs. The first is character probability. That is familiar to you guys. Basically what this is predicting what is the character being written at this moment. But the next is actually really interesting. Earlier we mentioned time warped principal component analysis, and they actually had to time warp their data earlier because writing an A at one time and writing an A at another time or writing an A at one time and writing another letter, for example, an X at another time, might take different amounts of time. And this network is time dependent. And so in order to account for this, previously they time warped it to make everything uniform. Here, they weren't able to time warp things because it wasn't efficient. So what they did instead was they added another output to determine when they were moving on to a new character. And that way, they could take as long as they wanted to write that character, and they would still be able to predict when the new character is being written, which I think is really cool. So testing was actually done over 3 days. And what they found was that on the first day of testing, they had completely trained the model and they tested it and they got very low accuracies. And the reason why was because of something called concept drift. So certain data sets, in this case, neural activity, change over time. And the trends stay the same, but the values themselves shift over time. And the statistical model that you might have trained may not account for that shift. And so you need to shift your model with the concept drift. And so that's what they did here with a recalibration. So every morning of testing, they would recalibrate their model up to 50 sentences. And as you can see, the character error rate dropped a lot. We also mentioned that they use autocorrect using a language model. And this was a pretty interesting idea, but basically a language model essentially is a model trained on a lot of a text of a certain language, a lot of sentences. And so what they used was GPT-2, released by OpenAI in 2019. This is a massive model trained on 8 million documents, scoured from the web. And this machine learning model knows multiple different languages. And so the idea was that if we were to, for example, our recurrent neural network was to predict, I am walking the DOD. We would input that sentence into our language model, and our language model would say, hey, I've never seen the word DOD in relation to any of these other words, but I have seen the word DOG. So it will replace the D and the G. And so using this strategy offline, so this was not in real time, they achieved a greater than 99% accuracy, which is super important. Maybe learning to implement this in real time might be really effective. So let's look at the results. Why is everyone talking about this paper? Well, they actually achieved a 90 character per minute speed with an online accuracy of 94%. So this is without the autocorrect feature, which is huge. 90 characters per minute is double the speed of previous records. And so what are the next steps? Well, there are 3 big next steps: scalability, efficiency, and longevity. Figuring out how to scale this towards multiple people, because a common challenge in BCI is to use the same machine learning model for multiple different people. The second is efficiency. There were 192 recording electrodes, which could be expensive and hard to implant in surgery. And so reducing the amount of electrodes might be important. And also longevity. A lot of these electrodes last 3 to 4 years. And so making sure that we develop electrodes that last longer, that last decades, might lessen the amount of work and stress that we put these subjects through, because they have to go through a brain surgery to get this implanted into their brain. But in general, I think this really shows a lot of potential for intracortical BCI technology in helping people with disabilities. So I thought I'd finish off by watching a little video of the model in action. Okay, here we go. So As we can see, there's a red square here. When the square turns green, he will start to type. And as you can see, his hand is moving, but he is not actually writing anything or having any of the motions of writing. These are called micro motions, and even though he is paralyzed from the neck down, when he intends to move his hand, he will be making these small motions that are not actually representative of the full, highly dexterous handwriting movements that he's actually intending to make. But anyways, as you can see, he's actually typing at a comparable speed to a normal typer, which I think is really, really interesting. This really has a greater application than something with half the typing speed. So yeah, that'll be all for me. Just wanted to say thank you to the reading program for giving me the opportunity to present this paper, and my mentor Jamie. Much love. Really couldn't have done it without your guidance. Yeah, I really, really love to talk about this stuff. So if you guys have any questions at all, just like send me an email. I'd happy to like have a discussion or something. And yeah, have a great rest of the event. See you later.